Last week there was no lecture. Next week also there will be no lecture because I'm unavailable. So I will require a date when we can transfer that lecture from the next week, because there is no option of like redoing a lecture. A lecture has to be transferred somewhere else. So I'm awaiting some proposals. It can be somewhere further down the semester and we'll just pick up later. Last week we've discussed main differences. Last lecture we discussed the differences between statistical modeling and machine learning, and we started moving about Bayesian methods. What are their general idea, how they became successful, what is the main difference between paradigm of classical statistical modeling and Bayesian statistical modeling, where the general idea is that the only certain things that we have is the data that we have obtained, and everything else is uncertain because of based on our assumptions, and that the data could be generated on the multiple different ways. So today we will cover the basics of Bayesian statistics. We'll give some few examples that kind of try to explain how the idea of Bayesian thinking is based on. So, main concepts of Bayesian data analysis is that we have a split of observables, so the quantities that we can actually observe, and unobservables, so the parameters of the actual process that is generating our data. We observed data which was created by a data generating process of some kind, including disturbances, including measurement techniques, representation of actual underlying phenomena that we're interested in, and how that phenomena generated those symptoms that we've measured as data. In our models we have parameters, we have data, and we have predictions. Predictions are useful because based on the parameters and knowledge about data, so our model, we can generate predictions of possible values of our models, which we can use to actually predict something, or just to understand how our model represents the reality. And those predictions can be understood in classical sense. That is, what is the value of, we want, like regression analysis, or they can be understood in more abstract ways, like, for example, predicted probability of events. Observing these kind of features, we predict that this event will happen with a probability of, let's say, 70%. So those are predictions. What is important that we consider observations as a complete collection of data representing one single aspect. Like, for example, one measurement might consist of just one number, but it might consist of a vector of numbers. Like, for example, when we are monitoring electrical motor, we are measuring the rotational speed, we are measuring currents, voltages, perhaps vibration. All those things are being measured simultaneously and consist one observational units. However, each of those values might be variables. Moreover, variables can be influencing our process, like, for example, control signal, voltage that we are feeding the motor, etc. Another aspect is exchangeability, because you know that there is an idea called independence of statistical events. That you should know from your classical probability, that events are independent. Events are not necessarily independent. This is a very restrictive aspect of that. However, they can be exchangeable. That means, for example, that we do not need them to be in order. If you observe something as a time series, like, for example, data of stock markets, they are, of course, not exchangeable individual point, right? Because they depend on the previous one. However, if you consider variability of the stock exchange data over the day, those individual days can be considered exchangeable because they are dependent on something else. If you have there is also something like called conditional exchangeability. So certain information are exchangeable if you know something extra. For example, if there are multiple tests on mice, given some dose of medicine to test how they behave in different laboratories, then those mice are not exchangeable because mice from laboratory A might be dependent on what's happening in laboratory A. So it won't be exactly the same. It would make a difference if we would put all the mice in the same bag and analyze the data jointly. However, within one laboratory, if we know that those mice come from the same laboratory, they can become exchangeable because they were in relatively similar conditions. So conditioning on the information that the mice came from one laboratory, individual mice are exchangeable. In the entire pool of mice in the experiment, they are not exchangeable. Clear? Okay. Explanatory variables, which are also known as predictors. In case of some classification analysis, we call them often features. These are values that we use to predict something. Those values that we measure, we introduce as our data as something that will be used to create predictions. They are inputs of our models. They are not the same thing as observed values of data, because data are something that we use to learn about what behaves. It's kind of obvious, but not always, because in certain data sets, in certain problems, you need to understand, well, what is the explanatory variable, what is our predictor, and what is actually a dependent variable that depends on those predictors or even values that we are interested in. So there might be situations when there is data that requires understanding which comes from which, some kind of causal analysis, what causes what. Important aspect is hierarchical modeling, that is creating a model in an increasing level of complication, including dependence on groups, or including something that we know that we don't know anything about the group that certain elements, certain, let's say, individuals in our population come from, but we know they come from the group. And there's also a different group that also has its own behaviors. We don't know what those behaviors are at the moment of inference, but we know that this is group separation. So we can create that, okay, individuals might be similar within group, but groups on the more abstract levels can be similar to one another. For example, if we want to model the preference for taste of ice cream on a group of people, we can group them to such groups like men and women, for example. And we can kind of expect that there are certain similarities between women and between men in kinds of their preferences. However, much less than the dependence between like individual women and individual men. So we could create a model that analyzes the behavior of gender influence, but at the same time, this aspect comes from the same group. They are still people, so we can assume that there are certain joint aspects, right, which influence the creation of those groups between men and women, and then we can model this like so. We can get a better fit some kind of model that represents women and men, and at the same time use it to advance the model that governs the entire population and their gender dependence. And finally, utility distributions, that is, and actually distributions of utility. Because in our operation, which we'll be doing, and we'll try to cover it at the end of this lecture, as an example, we are often not interested in actual values of predictions to evaluate our model. We are not really interested if the probability of failure is 0.7 or it's 0.8. Like, this value is not that relevant. What is relevant is what will be the cost of the device failing over time in the next, let's say, 60 days. So we can create a utility function that computes operation costs, how factory operates, and introduces this probability element that will be what happens if it fails, and on what time. And you introduce these simulations, they will be run, and you will do multiple simulations. So you have simulations that include failure, that won't include failure, failure at the end, failure at the beginning, depending on how your model is constructed, right? And because of the probability model, of course, this statistical distribution of those values will be some kind of representative of your knowledge about the model, about the process. Because that's why we're creating this simulation, not like we say, okay, it's 0.7, no. We created that in these conditions, in these operating situations, our model will, the probability of failure is, let's say, 0.7 today, 0.8 later, so on. So you can transform all these simulations into one number. For example, money. How much profit will be generated over the installation during these 60 days by continuous production. And in those, we will see what is the values, the probabilities, but instead of analyzing it as an average, because let's say, like, if you have a 1% probability to win $1 million, the expected value is $10,000, right? So it's a positive gain. But actually, it's not a meaningful value because it's still 1% chance only. So it's really like, in 1% chance, okay, you get the big money, and the rest of chance you get nothing. And in case of such simulations, you have, okay, 70% time we have, let's say, normal profit, and the company profits from the operation. But 30% of time there occurs a failure, and this failure is, depending on when it happens, costs us more or less. And you can then create a distribution, and you can see, okay, there is generally preferable situation, like for example using a histogram, that there's a good probability that everything will be okay, but there is this possibility that somewhere that will be a very significant loss. And for, let's say, computer simulation, it's not that relevant. Like when you are playing a video game where you have a percentage chance to hit something, like you hit something on average 80% time, for example, and that will be okay. But in case of business situation, when you have an 80% chance of normal operation and 20% chance of going under, then you have to reconsider this situation, right? So utility distributions are used exactly for that, to establish the distribution of actual relevant utility you get from your process based on the information you get from your model. So your model gives you the quantization of uncertainty you have of the quantities they're interested in, and the utility distribution will give you transferred to something that can be understood on a business decision-making level, or generally decision-making level. Generally, everything starts with joint probability. We are using a Bayesian probability, so we should derive the Bayes rule. And this is a very simple derivation. This is something that is almost high school level, depending on how high school looks like now. But generally, it is rather known that joint probability can be represented as a product of probability of one event, a conditional probability of the other, right? In case of observing that this is commutable, so either probability of one and conditional probability of the other, or probability of the other and conditional probability of the first one. So using that equality, you can easily represent conditional probability of one using the total probabilities and conditional probability of the other. In case of Bayesian statistics, we understood that conditional distribution of the parameters dependent on the data is the quotient of our prior knowledge of about parameters, the probability what are the values of parameters, probability of how our data fits the model based on the parameters, divided by the total probability of the data. Total probability is generally an average situation when of all possible data configuration over all possible parameter values. So how data fits all the possible values. So this is something that probably might be a bit complicated. Fortunately, that complicated part does not depend on parameters, and we are interested in parameters. That's why we work on, in most cases, on the numerator of this quotient. Denominator is independent of the value of parameters. So we can focus only on the numerator to get the relevant information for inference. So conditional probability of parameters conditioned on data we call posterior probability distribution, because this is the probability of parameters after we've added information about data, which is direct consequence of the prior information. So how much information we had about the parameters before we had any data. So we've talked last time, like we know, for example, that if we have a liquid in the cup, then this liquid is between 0 and 100 degrees. Because in other situations, it will be either ice or steam, right? So that's one thing. But also we kind of have other information that comes from multiple situations. Like the cup is not too hot to handle, so we know that it's somewhere below 36 degrees, right? And then we can add additional information. And finally, likelihood. Likelihood, which generally can be understood as how well the data fits the model given parameters theta. It is represented as a probability distribution, and actually a function that looks like a probability distribution, because this is not obvious at the first, okay? Because in all Bayesian computations, formulas sometimes can look exactly the same, but depending on what is a variable and what is the data, they completely change their meaning. So the likelihood function is, in the most basic sense, how well data fits the parameters. For given variable parameters, how well is the fit. And using this numerator, we can do actually a lot. And we can do a lot of reasoning on our computation. We will cover that in future lectures, how it exactly works. Quoting one of the most, let's say, notable Bayesian propagators now, Michael Betancourt, we can say that you should remember that using Bayes' theorem does not imply that you are using Bayesian statistics. Bayes' theorem works in all kinds of statistics and probability computation. This is a simple consequence of the, as a formula, it's a simple consequence of the joint probability theorem. What is actual clue in Bayesian statistics is the fact that we are quantifying uncertainty using probability. So we know that we do not know exactly something, but we can assign probability function as our measure of uncertainty, how well we know what's going on. Let's start with an example. The example comes from the book I recommended last time, Bayesian Data Analysis 3. This is a funny example, especially in the Polish context, because authors decided, okay, let's see what is the probability that when someone was writing random, actually wrote radom. Or in other words, if something if there is a word radom in text, was it meant to be random? So like they dropped an N from the word. And this is of course funny situation because first of all authors were from US and didn't know what radom is, which is not that surprising. And despite it having national navy shipyards, military navy shipyards are located in Radom. Despite it being away from the sea, this is actually a true story. There is a shipyard in Radom, at least the office building of the shipyard. Either way, the idea was, okay, let's simplify the problem. Let us assume that there are three possible words that we could use here. It could be random, what we wanted, radon, which is an element, and radom, which is, authors of the example didn't know that it's a city. But like they used it as a typically random word. So, what is the probability that we wanted to write random, but actual data said radom? So, using Bayes' rule, we have, of course, probably what is the general probability that it was actually random. So the prior probability, what is the probability that words written this way look like are random? Then likelihood represented as how possible what is to write random, conditional that we wanted to write random. And finally, total probability of all three cases. And they've used Google spell check model, and they found the first surprise that in English spell check model, word radom was not that impossible. Okay, it was less used than random, but only about 200 times less used. So that's not an impossible word, right? Still in English was less popular than radon, which is the word for element. Then, using the same computation, they've used what was the probability that we wanted to write radom, depending on what we wanted to write. So there are certain metrics used for spell checking, which generally they work only in English, and they are based on the keyboard distance. How likely, that's how automatic spell checker works, that's how autocorrect works. There are keyboard distances from the letters, how probable was to switch it to different letter. And it works in English because it works well with QWERTY keyboard. It doesn't work in Polish or in other languages that well. In Polish you have, and in Czech you have different characters that you have to use special commands additionally, which changes everything in this thinking. But there is the idea how to compute that, and of course, the highest probability, of course, is that using writing radom, you wanted to write radom, right? Because but what is the probability that you switch to the different word using those metrics? And you can then, using the product of prior distribution, so generally how common are those words in language, in the relative relationships, times the likelihood, computed using these keyboard metrics, then you can get the actual value of the numerator. So prior times likelihood. So the relatively high prior of random is multiplied by relatively low probability of making such mistake. With radon, mediocre probability of the prevalence of the word in the language was joined with small probability of introducing the mistake. And finally, while radom was not as common, 200 times less common than random, it was highly more probable to be written if we actually wanted to write that. So when you normalize that using sum of all those things here, because that's this total probability, you are averaging what word was intended, which is theta, out of that by summing it and dividing all those individuals by this sum, you get actual probabilities of certain things. And then, which could be surprising for writers of the book, random was not that probable. Most probability was still that someone wanted to write radom, which is twice as likely. However, because we were writing in English, still radom is not something often used, so still there's a 1/3 of a chance that it was a typo. Okay? So that's why we use the information about the language structure, so how words are useful. We used the metric of likelihood, how well the typo index fits here. And finally, we've averaged it out to get probabilities. And we don't get actual number, oh, you written radom, but you really wanted random. No, you get uncertainty. There is 67% for radom, 30-something% for random, but there is still 0.2% for radon, which might be relevant in certain cases that it was a shipment of a radioactive substance, and if someone made a typo, we shouldn't ignore that, depending again on the utility function. If we are screening mails for, let's say, terrorism, the cost of introducing a radioactive element in large numbers to civilian areas to create a dirty bomb, then the utility cost of such shipment being skipped is very high. Then, despite the event has low probability, it's not impossible, and it's very costly. So if it's not impossible, perhaps we need to check it out anyway. Okay? You understand those concepts? Utility, probability, uncertainty here? Great. So again, we've, in most applications, focused on the numerator because denominator, in our case, was just a normalizing constant. If we wanted to see which has most probability, we could choose it anyway, which is the biggest value, right? By the denominator, because they are still divided by the same scaling factor. if we want to analyze which is more likely than the other, we can divide them by each other and get that. And also, in order to do computation, in most cases, likelihood, the numerator will be enough. Okay. Some crucial Bayesian concepts that we will be using over the entire semester, you will be using in your project, etc. First of all, prior predictive distribution. In case of Bayesian statistics, we actually can, using our proposed structure of prior and likelihood, we can determine what kind of data we can expect. Even before the experiment, we can see what data we can expect, which is actually very useful. Prior predictive distribution allows us, so creating a distribution of data that can happen is a very useful thing. Because if we can then test our assumptions of how our model makes sense. If the data that is generated by prior predictive distribution is completely impossible, then our model is wrong. And we can do that even before we started using actual data. That's one thing. So this is for testing the assumptions. We know something about data, we can test how our model will, if our model will be possible to capture that data. If the data comes from, let's say, certain area, certain space, certain values, and our simulated model does not generate that data at all, or even similar, because it's not a point to have it prior to generate exactly the data you have. This is a common problem with your projects, that you try to fit prior so well that it will fit the data that you already had. You shouldn't actually establish prior using data, but you can look at the data and see if they were possible in the prior context. Because then you see, okay, prior is not, is bad. Second thing is that sometimes prior is good by its general implication, and can be used to plan the experiment. Because if you have prior predictive, if you construct a prior predictive distribution, you can see what kind of data will be needed for you to get some kind of information that you want. You can get what kind of values will be relevant for your scope. You can test, okay, using our assumptions, we know that certain aspects can be observed only for given values of predictors. If we don't get those values, then we won't observe what we want. So we can plan the experiment to get enough information for that. We can also generate data that we can then use to train our model and test, okay, using given configuration of the model, we can generate data, and that data will be enough to recover the model configuration information. It's like, the idea is that there are situations that in certain experiments you won't be able to get anything. For example, if you put an electric motor in an idle run, so it will be running with constant speed, you won't get any information about its dynamics, right? Because that dynamics is not present in the data. So you can, using prior predictive distribution, you can check, okay, what kind of data we can get from that. And this, of course, looks horrible because it looks like a big integral and of unknown functions, because you want to integrate parameters out of the joint probability distribution, or in other words, integrate out parameters from the product of likelihood and prior. Because you integrate them out, you will get function that will depend only on data, on y. However, practical use of these things is based on is that you can very easily generate samples from this distribution, or at least proportional to this distribution. So generate sample data just by simulation. And if you do that enough times, randomizing theta and using that random theta to generate y, you will get a lot of samples of y, which can be used to recover the distribution. So you can generally perform, it's called Monte Carlo integration. In particular, you just get a simulation of samples of y, which you can then analyze, for example, as a histogram to estimate its distribution. And this is a tool that we will be using a lot. This is called marginalization, so getting a marginal distribution of certain variables. In classical probability, you have to integrate everything by integrals. In computational statistics, you just simulate and drop everything you are not interested in. So this is very, very useful situation. Consequence, because we can work this way, we have also something called posterior predictive distribution. And posterior predictive distribution is an idea that, okay, if we can sample from the probability model having a prior distribution on theta to generate data that could happen, then why not use the information that we can obtain from data that we already have? So create a model that will give us the conditional probability distribution of theta depending on y. So our typical Bayesian inference, and using that distribution, sample theta from that, sample values from those distributions, which is generally something that we'll be doing anyway, and then use this sampled theta in likelihood to sample new values of y. Then we won't be sampling data that comes from the simulating data that comes from the assumptions. We will be simulating data that comes from the assumptions adjusted by our data. So we will be observing what kind of data we can get from information that we've already obtained. And this is something that generally is called a generative model. Bayesian models are naturally generative. So they can generate new data given some data and some assumptions. What is the most popular generative models that we know? I'm sure that you have already used that at least once. ChatGPT exactly is a generative model. And ChatGPT is actually a probabilistic model. And in certain way it's a Bayesian model. But there's a certain computational tricks that are happening there that explain why there exists a neural network there or something like that. Because there are actually, especially with these reasoning aspects, everything is really typical Bayesian reasoning. This works, it just works on words, not on numbers. That's the only difference. And those words can be represented as numbers in certain sense, so that's not a problem. Generative models are very useful because having some information, you can generate new data and, for example, use it for utility functions to establish what will be the profit. We see that, okay, from this observation we already have, we think that parameters of our model are this. Knowing that, we can sample from that. Model, and we can make some decisions. And then, simulating data, we can confront them with those decisions and see what will happen. And get a version. I wanted to do this example at the end of the lecture, but I think we should do it now because it explains, I think, more. The idea is from automatic control. Very classical problem. We have a step response of the, we have a system with a step response. Classical automatic control problem, right? We want to estimate how the, what are the parameters of the model. And we can do that by observing some data. So we can have a step response and we can observe some data. And we are accustomed to a situation that we have very good measurements, a lot of measurements. This is not always the case. So let us consider, and why we want to do that? Just to be clear, we want to design an LQ controller. So the optimal controller that will be used for this system that will stabilize it in zero in an optimal way. And for that system, in ideal case, with these parameters, this controller will work generally like this. So the output of the system will behave like this from some kind of initial condition, and the trajectories will behave like this. Right? Simple. Okay. Let's generate some data. We have a lot of measurement noise, and noise with the variance of 0.2 in the scale of parameters, which comes to the gain of the system is 0.6, so this is a large noise. We have 10 samples. We can use Bayesian computation to estimate those parameters. We are using something that we'll be using in this entire course, which is STAN. STAN is probabilistic programming language. We'll talk about it later, but let's start with an example. We have a model that includes data, time instances where the data were measured, and measurements, which were measured with some kind of error. We have n samples, which is needed because STAN is not as dynamically typed like Python. You have to give the number of sizes of arrays and stuff like that. We assume that our model, because it's stable, so we are adding assumptions. First of all, we are assuming that standard deviation of measurements, of course, is positive, because standard deviation is always positive. And A and B, the parameter is always also positive. Why? From Hurwitz criterion, second order system has to have positive coefficients of the characteristic polynomial, right? Otherwise, it will destabilize. So, we then need to compute the step response to compare it with the data. So for this purpose, we are computing the roots of the polynomial, we are computing the discriminant to switch it from real or either it will be real or there will be complex poles of the transfer function, so either will be oscillatory system or not, so we have to be prepared for that. We compute the roots, we compute the step response, either without oscillations or with periodic aspects or without periodic aspects. Some oscillation cannot happen with real poles also. But those will be like, depending on which exponent dominates from the beginning. So, depending on which case it is, we compute the values of predicted y in points given by our data, right? So we'll have this is needed for our computation of likelihood. That is, how well our data fits our parameter. For given parameters, we can determine the values of y that should come from the output. We assign prior distributions. This is a trick in STAN, which is not that obvious. That is because we've assumed that A and B are positive. This changes this distribution. This is not a normal probability distribution. It's a half normal probability distribution. This is a trick of STAN. Half normal probability distribution is like a normal distribution, but cut off on the left side. So all negative values are removed, and that increases a mass of probability somewhere, just to be working. Generally, it's equivalent to simulating a normal variable and taking the absolute value of it. This is generally the same, but this is how it's being done in Stan. So we are specifying these half normal distributions for A and B, and we are providing a prior for the standard deviation, and we are using Cauchy distribution, which is a specific distribution that is actually a half Cauchy distribution again, because we have assigned it from 0. This is a distribution that generally is centered around 0, but can allow big numbers. It is so-called heavy-tailed distribution, if you heard about it, for example, in context of black swans and stuff like that. And our model is very simple. We say that our data is distributed as a normal distribution centered in our predictions computed above dependent parameters with standard deviation sigma. This is, from computational point of view, practically equivalent to a nonlinear least square problem. We have nonlinear dependence of parameters on the outputs, because it's this with true exponents and roots of polynomials, right? And then we put it in the normal likelihood. We can formalize in multiple different ways, also in Stan. Generally, it means that what is the probability that our data is consistent with the model for given number of parameters. This specification of the model is then treated using Stan, using Hamiltonian Monte Carlo computation, which is a class of Markov chain Monte Carlo methods of computation, which we will explain somewhere later in this course. So, in very brief, it will take this model in this Stan language. It will then formalize into some kind of graph that describes how the computation is being computed. We'll use automatic differentiation methods in order to create derivatives of this graph, in order to create certain differential equation that will have to be solved online, and using that we'll generate samples from the probability distribution of generally from the joint probability distribution of data and parameters, but joint probability of data and parameters is actually proportional to our numerator of conditional probability, right? Because just from the definition of conditional probability or definition from the joint probability, however you look at it. So it will generate those samples, and we'll cover it how it's being done and all different methods later. So we will be creating 4 Markov chains, so we'll generate 4,000 samples, because each Markov chain will have 1,000 samples of parameters, which we will generate using our model. Model is here the model is compiled. It creates instance of model using command stanpy, which you already should have on your laboratory classes before, which works in a way that generally command stanpy is a wrapper over command stan, which is a wrapper over actual stan. Stan is this language that is platform independent but requires interfaces. You have rstan for R, you have PyStan, you have armstan, stanarm, you have stanarm for also for R, you have the different wrappers on that, and for Python you have either PyStan or you have command stanpy, because command stan is a wrapper for command line. So it works like this. It generates Python code that calls command line interface to stan, generates data in form of CSV files, in temporary files, and everything is being then put into memory in case as a proper object. You can also save all those intermediate results if you want to in special folders, so that's not a problem. We are using command stanpy because from my experience, is most robust of all those solutions. Well, like rstan is okay, but you hate R as students, so we are not using that. PyStan is perhaps, supposedly it's better now, but from my experience it was notoriously fickle. It could break on system updates. This also can break on system updates, especially on Mac, but it's relatively easily fixable. And you can also get information, you don't lose information that easy as in PyStan. But maybe we'll switch sometime. Or maybe we'll switch from Stan altogether into PyMC, but I'm a little bit shaky about that. PyMC is a purely Python environment which does generally the same. Certain theoretical advances are being slower to adapt in PyMC. PyMC is a bit slower because it works using Stan. Stan compiles to C, and everything works in C. PyMC uses Tiano, which is one of the less known machine learning frameworks, like the neural network frameworks, but they've acquired it and integrated it into their system because it also allows you automatic differentiation in certain aspects, and does a lot of work in Python, and then, of course, like typical models in machine learning, it also does some kind of lower compilation later. Generally, in order to do some inference, because it can be time-consuming. The issue is that, from my experience, or maybe experience, maybe more intuition, PyMC will be much less friendly to students, especially when working in Jupyter notebooks, because in Stan, you create your model encapsulated in individual Stan files. So there is no risk of overlapping variables between two languages, namespaces being collided, and stuff like that. In case of PyMC, models are being specified using context managers. And it is irritating because you can use both normal NumPy variables and special PyMC variables in those context managers, and sometimes they are visible outside of it, sometimes not. And that can make debugging, especially when you are using Jupyter Notebook and skipping one line over the other and running cells as you wish, can be very difficult to debug, especially during classes. That's why we are using Stan, because it's a bit better and it's more student robust in the case of education. But that's it. Either way, that was a Stan interlude. Let's come back to our actual model. So we are providing the data, n samples, time instances, data from the step response. We perform sampling. I will run it again in a moment just so you can see, but first I'm showing you a situation where we have a lot of data, relatively lot of data. The sampling is very simple. It samples all the parameters, A, B, sigma, and generates those values, which are being stored into certain data frame, and we can estimate those values. If someone was curious, true parameters that we used to generate data were 1 and 2 for A and B. So here, it's not that far as a mean value. Looking for the is here. The mean value is relatively close. We can then see how our model actually fits our data and what's the inference. So we can get predictions of y using those parameters in those points, and we can see that they do not fit the data that we observed that specifically well. Why? Well, because we've introduced very strong structural relationships between y and parameters. And those values couldn't be, those here, couldn't be directly generated all by that data. It has to be taken under some kind of noise, which we'll be modeling here, and we will also estimating the noise parameters. So, this looks like this. So we can compute our linear quadratic controllers. And we can use that using the mean values of A and B from our model. And using it for our real process, here without disturbances in the measurements, we can see it performs relatively well. Mean values for the actual process. This can be considered some kind of a success. However, we can now look at the case of the utility function. We have a natural utility function, which is, of course, the linear quadratic performance indicator. That is the integral of the square of the state. In here we use the unit matrix for it, so both state variables, squares of them, and u also square of it. So those things are here. And we'll compute the statistical analysis in the case of what is the actual value of the performance indicator depending on all the possible depending on what we know about parameters. So we can get the knowing the actual values of the system, we can compute how the gains computed by different estimated parameters would generate a performance indicator. We will also compute what the model what is the estimated performance indicator depending on the estimated values. So look at it like this. We have at the moment 4,000 sets of parameters AB. This is how Stan works. We have 4,000 parameters AB. So we have a sample from the population of all possible parameters AB, which are consistent with the data and observe uncertainty. So we have 4,000. If there was no uncertainty, there would be just the same number all the time. If there is uncertainty, we have different numbers. Okay? So we have, if we took those parameters individually and computed gains, what would be actual value of performance indicator? What is the performance indicator value estimated for the gain that can be obtained? So like if we wouldn't know what are the true values, we could still estimate using LQ what is the performance indicator value for those gains that we've computed. We get A and B, and for those, so we will have a distribution of possible value of performance indicators consistent with our knowledge. And finally, we will have how much we lose using that knowledge if we use the mean values for the gains. Because when you take one number for A and B, you discard some information, right? You've selected one number to represent all the possible values of A and one number to represent all possible values of B, right? So, in that case, using those values, you can get we can observe what is the predicted loss of using that mean value corresponding to all the knowledge that we've extracted from the model. And we can observe it using histograms. So, let's start with what are the possible values of performance indicators. The red point is the ideal situation. What would be a true optimum for the true system? Something that we've computed, that generated the first plot we have above. So we can see that we assume from our data that the performance indicator value, maybe I can a bit reduce it because it's, okay, it will be more visible. We get certain skewness here. From the data that we have, we would assume that would be better generally. And we also see that it is possible to get values even twice as bad as the optimal and almost 2.5 times bad as the best that we can observe. So we see that, okay, using the knowledge we have here, the actual performance indicator can look like this. These are all the possible values. If we reduce just to the mean, it will be shifted a bit. So possible values of performance indicator can even get to bigger numbers, right? Actual plot of difference look like this. So this is how much we lose from our knowledge using our prediction of the data. And true performance indicator distribution looks like this. So using this is a very good information. Using the data that we have, the model parameters that we can obtain, we don't lose that much from the optimal value, right? Because for the true system, we can't go better than this. This is a true optimal value for the true system. And these are how worse it gets by using the information that we got here. That actually shows us that LQ is a very robust control strategy. LQ with observer, with Kalman filter, is not a, but it would be too complicated model to show you here. But because that one can break very easily. But just LQ, if you have real measurements, then it's very good. If you have LQ with Kalman filter, it can break. So especially with large noises, this can break really easily. And finally, we can look how our parameters look like here estimated. So we can see that we are relatively close to true values. And our standard deviation is also consistent with standard deviation of the data that we have. But we have 10 samples over some period. Let's see what happens if we have less samples. So I'm changing the sample numbers to 3. Run all. The code is not legible anymore, but figures at least we can see. Okay, so of course open loop doesn't change because it in true looks like this. This also doesn't change, but we have only 3 samples here, right? Here, here, and here. They come from the model with the same standard deviation. We have much less data. It is possible that at such situation, yes, of course, depending on what the process is. Sometimes we have getting data is very costly. Like taking a complicated measurement process that requires, for example, we have a chemical reactor, someone have to have a bucket, take the product to the bucket, take it to the laboratory, analyze it, see it. So it can be difficult. So you have limited number of measurements. Again, computation looks very similarly. This does not necessarily look like something that we had. But, again, robustness of LQ is astounding because, as you can see, despite the fact that you get errors in the modeling, the LQ gains still are kind of rather good. The dashed ones are the ideal ones, the solid ones are the new ones. Okay? And this is how the assumed distribution looks like. And here we have a lot of uncertainty. Previously it was kind of focused somewhere here. We really have a large spread of possible values of performance indicator. The range of possible values is similar, but as you can see, we kind of expect that it will be much worse because we have much less data. We look at completely different system when you analyze it, right? Okay. If we use the mean, the change is not dramatic, but we can still see that there is certain shift here of possible gains. Here's a bit closer to this side, how it looks like, okay? Because there are different axes here. It starts a bit more to the left. So using the mean introduces some cost, but not that much. And possible values here of differences. So those losses can be still are not horrible by introducing the mean, but are kind of like bigger here and more distributed. So previously there was a big spike in 0. Here the spike in 0 is relatively small. And this is how true model would be distributed. How the loss would look depending on which sample from A and B we would choose. Of course, it still cannot be worse than here, right? But it cannot be better than the optimal value. But as you can see, we have a lot of uncertainty what's going on with the performance indicator. So here we can see that having so little information, the controller that we propose, the LQ controller, can be okay, but it's actually we expect that it will be much worse. This is a better situation that we expect that it will be much better, but we can easily expect that if the noises would look differently, we would get a completely different situation. We have an expectation for a much better result that it comes, but still look like in all those cases, true result is always possible. And let's look at parameters. In case of parameters, we see that it expected completely different value of A, much smaller, right? Relatively close value of B, but here's the point. Previously, we had the standard deviation much more constrained. Here, it kind of assumes, okay, the model is bad, but we have a lot of uncertainty in the measurements. Okay? So we have a lot of possibility of different situation. Okay? Understand that? Hopefully. Okay. So, that was the most advanced example that we can see that how the utility function is used. Our simulation of parameters, the samples of parameters, allowed us to create a distribution of performance indicator. We could also create a distribution of trajectories. We just have to run a lot of simulations, but here we skipped that part because in case of LQ controller, we can compute those performance indicators by formula. So that's what was used here. But we've created a utility distribution that based on posterior predictive distribution to estimate what are the possible values of the performance indicator. Okay. Let's come back to our slides. A few additional notions that need to be kept at the behind of your head. First of all, everything is conditional. So all our assumptions, all our prior distribution, everything is conditional on the hypothesis that we have. We don't write it explicitly because it will be lots of letters, but all assumptions that you introduce to your model that are included in priors, on the likelihoods, and somewhere else, are dependent on what you've planned here. So that is, you should be aware of what you are putting inside your model. That's why Bayesian modeling is not a black box automatic thing that you can run and will be always better. No, but it allows you to put things into this model that you know already, And if you do it properly, you add those assumptions and will allow you to shape your response better to your expectation and actual situation. However, if you do some implicit assumptions that you won't clearly state, you can go to errors. That you can, for example, introduce that certain bounds on variables. Let's say implicitly assume that certain variable is positive. So you've assigned it a prior distribution that takes only positive values. And that will make your model stop working or lead to bad conclusions. So that's important situation. However, it can work other ways by introducing stiff bounds. For example, if you introduce your assumptions properly, when you know that the value that you want is always positive, but you get a negative value, it won't be reduced to 0. You will use the information about the measurement noise to estimate that, okay, if this value was negative, observed, and the noise that can be positive or negative has a large variance, so in that variance, okay, it cannot be too big, but still it had to be positive because it happens. So you have to adjust that idea properly. Additional thing, of course, the thing that will be interesting in mods is the expectation. The expectation is the function that we will want the most, because using expected values of multiple different functions, we will be able to do an inference. And these expected values are very simple to obtain by sampling, which we'll cover later. Variance, of course, is also, in a sense, an expected value of something else. Conditional expectation variances, we'll cover that with simulations, so we don't care that much. Changing of variables, this is something that is very hard in especially complicated analytical computation. If you have a discrete distribution, it's easier. If you have continuous distribution, it's harder because you have to use differential transformations using Jacobians in order to get different distributions, especially if there are multi-dimensional situations, then it's very difficult, especially if you move from, like, for example, you want to transform two variables into one, like, for example, an average of them, or geometric mean, and because it's, or like convert two parameters into a distance, and that makes analytical computation hard. In case of numerical computation, it's much easier because it kind of happens by itself. You can generate data from untransformed data and then transform it later, and it will also work. However, variable changes are something that we are using very often because sometimes we just have variables that are constrained, and it's much easier to introduce a continuous, smooth variable change than to introduce hard constraints. Because, as I mentioned, we will be solving implicitly some differential equations. And differential equations, when they hit into the wall, they have problems. So it's much better to create, instead of a wall, a very steep curve that will push them away. So, important logarithmic transformation that will allow us to transform from real numbers to positive numbers or other way. So, very important aspect. Sometimes we just need to work in positive numbers and we don't want to get any negative ones. And of course, sometimes we just want to work on different orders of magnitude, like salaries. Salaries are on different orders of magnitude. You have people that are working on minimum wage, and you have Elon Musk. And all those people are the same system generally. So, and they are on different orders of magnitude. Logistic transformation is from 0, 1 to real or inverse in a case. Very important in case if you are interested in data that is probabilistic. So you have value that between 0 and 1, but the probability logistic transformation will allow you to transform something in this way. This can be as easily done as logistic regression that we've covered in the data analytics course in first degree, or it can be more advanced. You have also probit regression, like a probit transformation, and others, which can be very useful, and probably we'll be using them somewhere later. Very often we will try to use simple single parameter models in order to get some kind of building block of a larger model. Simple one parameter model can be, for example, difference between treatments. It can be probability of something, what is the effect of something. There are multiple single parameter models that can be useful. The most simple one is the binomial model. The single parameter is the probability, and we want to know, will something happen? Coin flip, heads or tails. Exam, pass or fail. Sun, rise or not. Was Earth destroyed? Or wasn't? Probably wasn't. We have two outcomes, success and failure, often coded on 0 and 1. All is dependent on, in case of binomial probability, in a sequence of trials, how many successes occurred. Special case, one trial, Bernoulli distribution. So, depending on the one parameter probability, we can assume we can create a model that will say what is the probability of y depending on theta. So our likelihood, knowing theta, we know what's the probability of given y. Y in this case, number of successes, integer number. Example, somebody of you played Mass Effect? It's a relatively known space RPG. There was a legendary edition of like 3 games together, and there was the less fortunate sequel called Andromeda, and there is also something is coming relatively soon. It's from EA. One of the mini games in this game is scanning of planets for resources. We'll just do it in the most simple way. We'll try to probe for water. So we have the planet that is spinning. We are dropping a probe on the planet. It will either hit water or not. It's much easier case than coin flip, because coin flip requires some kind of skill, right? That it can drop on the edge and so on. One of the examples that I've tried to use in these lectures is throwing a ball with the globe ball. It's surprisingly hard to buy a ball that is soft and has a land on it with seas and can be thrown at it. I managed to buy one that was such small, like an apple, which is a bit too small to use in the class. And beach balls are too big, so like finding something more average was difficult. So I've dropped doing that, but it was also easy because you drop something, you put a thumb on it of your right hand, it will be either on water or not. So we could do an experiment. Generally, so in this case, localization of a probe will give us either a success or a failure. And of course, each toss is independent from each other, because here it will be much more difficult to, like, repetitive skill of catching something like that, especially if you are tossing it in the class, right? Okay. So for example, if we have multiple, let's say 7 successes in 9 trials, the likelihood will look something like this, the probable values of, depending on the parameter theta, will get different likelihood values of it. So how our model will fit. The bigger value, the better, or the more probable. However, remember that this is not probability, this is likelihood. This is just a number. Also, individual number in each point means nothing, because it's a continuous distribution. You need consider the area under the curve. Analytically, assuming that we know nothing besides that the theta is between 0 and 1, so this is called uniform prior, we can compute the posterior. And this is actually an interesting case. this is posterior, which is proportional to such product like here, right? This is likelihood. It looks exactly the same, right? This is a constant here, which is independent of theta, so it's also proportional. Why one is likelihood and why the other one is posterior? The likelihood is function of y dependent on theta. The posterior is function of theta depending on y. So in this very simple case, with assuming that we don't care about the scale, so the probability, so we are not caring about a constant that will be scaling it, likelihood and posterior are exactly the same function but with different understanding. In this function, theta is our independent variable that we are interested in to get a probability of given theta, and y is our parameter of this function, is our number here, our data point. Here, for given value of theta, we could compute probability of that y happening, okay? We haven't switched anything except our understanding of this formula, okay? We use the same formula for different thing, but it looks exactly the same. And because now our dependent value is theta and our independent is y, it's no longer a binomial distribution, because binomial distribution was a distribution on integers, right? The probability of given y. Theta takes real values between 0 and 1. So it gives you a probability of a continuous variable. And in this case, theta is actually a known distribution called beta distribution, which is defined this way. We like use known distribution because someone did all the computation for us already. So we know means, standard deviations, variances, medians, stuff like that. Those things are known. So we can use formulas already and we don't have to compute anything by ourselves. Either way, using this change of thinking about the same formula, we moved from the binomial distribution to a beta distribution, which differs to each other only by a scaling factor. Okay. So we have posterior. How to move from the posterior to some kind of a decision making? Because let's be clear, we not necessarily can make decision on given functions, right? Especially on the business making. So the best summarization of our probability is, of course, the posterior by itself, because it gives us all the information that we want. What can happen, what certain values are possible, etc. However, usually we want to get some kind of number, and this number will be either mean, which is simple to understand, but sometimes flawed, like for example during salaries, median, which is more robust but less understood by everyone, and mode, that is the maximum of the probability distribution, so which point is kind of the most likely. This, if we have a normal distribution, those three things are the same. If we don't have a normal distribution, and in case of Gaussian, Bayesian computation, it will happen, they will differ. And of course, we want to kind of get this number some kind of uncertainty. So we add some kind of measure of variation. Usually standard deviation, if something is kind of normal, or intervals. The easiest intervals are, of course, related to standard deviations. That is, it's plus minus 1 standard deviation is 67% probability, plus 2 is 95% probability, plus 3 is 99% probability. In case of, if we want others, we can use quantiles or quartiles. So like the given probability intervals, like median is a center quartile, so we can want something else. However, we do not have, we are not limited to that, so we can use generally some kind of interval summaries. So for example, we want to have a central interval that will have 94% probability, then we can of course compute it. However, it's not the only option. A different option is highest density interval. So the smallest interval that will consist of 94% probability, but it not necessarily has to be a compact set, because it can be split here. The smallest interval here will be sum of these two, right? So we have multiple options of summarization. And we've covered this globe tossing example with a very simple prior. We assumed that we know nothing. We just know that there is equal probability there will be 99% water or 0.1% water or even 0% water. And that is prior. Selection of information that we introduced to our model before our computation. And I think because it's 2:45, we will end for today with our lecture, and we will continue in 2 weeks. Because next week I am not available because I have a defense of a PhD that actually I have to head over the committee that does that. So that's it. Okay, just to be